about arrays. Abstract arrays. ADT stands for abstract data type. Now the abstract data type array, and you're used to it being implemented in a programming language as a block of memory, has only two operators, fetch and store. Now, when you do fetch, you're querying the array to obtain a value that's stored there. So you have an array and you have an index, which is typically an integer, but if the array is something else like multidimensional, perhaps the index could be a pair of integers or a triple or whatever. But in any case, you fetch this value by inputting the name of the array and the index. Then on the other hand, you can store a value, and we're assuming that these values have type. They don't have to be integer. We'll assume there's this type which we're going to call item. And we store in an array at a particular index the value of the item value x. So that corresponds to an assignment like this. Now the important thing is there is a standard implementation of array in programming languages. And in fact, the entire memory of a computer is actually one giant array. However, these rules don't require you to implement an array in that manner. We're going to look at some other ways to implement an array. Okay. All right. Now let's talk about a sparse array. A sparse array is an array where there are not too many elements that are not, say, 0 or whatever the default value is. Maybe it's null or something else. But here's an example of a sparse array. So we'll call it A, and it's like size n, but it only has 3 elements that are not equal to the default value, which is typically 0. And you could store this array as a regular array. On the other hand, maybe it would be faster to store it like this. Just remember that A of 1 is 3, A of 7 is 7, A of 12 is -5, and then you simply have the rule that all others are 0. Now, if n is large enough, that could actually save space. When we have a sparse array, one way of representing it is to use a search structure. Here I'm using a binary search tree, where the index, of course, is the index. And every element of the binary tree is an ordered pair, such as the array A of 5 equals 21, and A of 3 equals -4, A of 20 equals 4, and so forth. Now how would you store this array? Well, it goes all the way up to 41 and starts at 1, so you need 41 spaces. However, I probably don't need 41 spaces to store the structure. So how would I utilize this binary tree storage? Suppose, for example, I wanted to fetch. So let's say that the default value is 0, which is typical. And I ask the question, I want to fetch A of 7. All right, so I search for 7 in the binary tree, and it isn't there. So therefore, I return the default value. The default value. If I want to fetch A of 17, I go like this and I search, I find 17, so I return 100. Now, if I want to store something, for example, I want to execute a statement like this, like, for example, A of 4 equals 10. For example, now I would search for the number 4 in here as an index, and it doesn't exist. So therefore, I would insert this pair, 410, into the binary search tree. On the other hand, if I wanted to say A of 20 equals 6, I would search for it and I find there is a 20 there on the index, so I would delete this, I would overwrite it with a 6. And this is how I would implement a sparse array. Now the word sparse is a relative term, like big or fast or easy or anything like that, where it's kind of a relative concept. Big is not an absolute term, and fast is not an absolute term. And neither is sparse. But in this case, using this technique of storing pairs into a search structure, we would think of it as sparse if this method of storage is more efficient than storing it just explicitly as an array. So we'll take that as a practical example of what we mean by sparse. Now, a search structure is any structure where you can insert items, delete items, look for items, search for items. Now, what I drew on the previous slide was a binary search tree, which just comes to mind automatically. Another kind of search structure is a hash table. There are various kinds of balanced trees and other balanced search structures, but one of the most important search structures is one that you would never think of, and that's an unordered list, just a plain old list which has not been sorted. Now, in order to search for an item in an unordered list, you have to do linear search. Look at every item until you either find the item or get to the end of the list. Is that ever efficient? Sounds inefficient, doesn't it? Well, the fact is that it's sometimes the most efficient thing to do. And when does that happen? That happens when the number of items in the list is very small. And remember, small is a relative term. So if there are only 5 elements in the list, it's not worth it to set up one of these sophisticated structures, because the cost of setting that up is greater than the cost of just doing linear search when you need an item. Now, for example, let's look at sparse arrays here. We'll call this array sparse. Now, the general idea of sparse is that there are lots fewer items than there could be. So this is a 6 by 6 array, which has 36 spaces, but it looks like there are only 5, 8, 10, 11 non-zero items in there. We're assuming that all the blank spaces are the default value, 0. And on the other hand, this one is very sparse, not only less than 36, but also less than 6. This has only 3 items. Now, if you were going to store an array like this, you would use a search structure which would hold triples like this: 2, 3, 2, 4, 5, 1, and 6, 3, 5. In other words, there's a 2 in position 2, 3. There's a 1 in position 4, 5, and there is a 5 in position 6, 3. And you could put those into a search structure and do it the same way you did a one-dimensional sparse array. On the other hand, for an array that is sparse but not very sparse, there's an alternative method. Now notice that what's happening here is each row is sparse, but the number of rows is still 6. There are still 6, or maybe there would be almost 6 rows. And you can save space and effort by making this into an array of search structures. For example, you would get an array here of sparse search structures. Now each sparse search structure could be any one of those search structures, a binary search tree, or perhaps an unordered linked list. So that means that we would have an array here, arrayed one object for each row, and then inside that we would have a list perhaps of the items. So this would be 2, 3, and 4, 5. 4, negative 5. Then the items here would be 1, 2, and 5, 4. And the items here would be 3, 1. And this would be 1, 6, 2, 7, 6, 12, and so forth. 3 minus 3, 4, 4, and I guess it would be 3, 9. Of course, it could be that there's an empty row, which is perfectly okay. Then it would be an empty search structure for that row. And once again, we would do fetch and store the same way I showed you before, except for the fetch or the store, you would first do random access to the correct structure using the old-fashioned method. So this would be row 1, row 2, row 3, row 4, row 5, row 6, implemented as an array in the built-in manner, but the objects of the array would then be these lists or search structures somehow.